Okay, let's take a look at Chapter 12. We're going to do the notes as video notes and a few homework problems tonight, and then we'll have some worksheets tomorrow, or actually the video note or the notes from section 12.3 and 12.4. Okay, this chapter is on sequences and series. It's the last chapter of the year. A sequence is a list of numbers. Each number in this sequence is called a term of the sequence. Each number in the sequence usually is labeled according to what term it is. A sub 1, A sub 2, A sub 3, etc. A finite sequence is a sequence that has a definite ending. More formally, a function whose domain is the set of positive integers less than or equal to some fixed positive integer. So for example, this goes from a sub 1 to a sub 6, and then it stops. When we look at an infinite sequence, it will go from a sub 1 to a sub n. So here we have a sub n, and we'll see these three little dots after a list or a sequence of numbers that will indicate that it continues on. Some things to note about sequences is we usually use n as the independent variable instead of x, since n is the set of natural numbers. Now you also see in some textbooks it's represented as I, can be represented as k. You'll see when we look at the summation notation where that shows up and how to know that that is the variable. For the dependent variable, we usually write a sub n rather than y. A sub n is the nth term or the general term. Looking a little more specifically, listing the terms of a finite sequence. So let's say we are given the sequence where a sub n is equal to 4n minus 3. Looks like there should be an a sub 1 there. So finding those terms, I'm simply going to substitute the value of n in, which is, the first one's going to be n times 1. So that will give me 4 times 1 minus 3, which is 1. A sub 2 will be 4 times 2 minus 3, which would give me a 5. A sub 4 is going to be 4 times 3 minus 3 equals 9. I don't know what that is. And then a sub 4 is equal to 4 times 4 minus 3, which is 13. So all you're doing is substituting the value in for n, listing the term. These are the terms. And then you substitute that into the formula so that you can get the value of the fourth term, fifth term, sixth term, whatever term you're looking for. Here's another example. Find the first 4 terms of the sequence 2 plus negative 1 to the n. So when I substitute in the 1, now n is the exponent, so what you're going to see is this just oscillates between two numbers. So this becomes a 1, and then 2 plus minus 1 squared will make that positive, which will make that a 3, and then 2 plus negative 1 to the third. So it's odd, meaning that that negative 1, that's 2 minus 1, which is 1. And then the fourth, 2 plus negative 1 to the fourth, again will return to even. So if you're looking to find those terms in a sequence, again, these are the terms. We're simply substituting in from some starting point to some finishing point and finding the value of each of those terms at this point. We'll add them up later. We'll find the sum of an arithmetic and the sum of a geometric sequence in sections 12.3 and 12.4. Finding a formula for the nth term. So what you're asked to do is write the general term for the infinite sequence. So when you look at this, you can see that it increases by 2. And all of the terms are odd. When I see that, it makes me think I can take a number and double it and add 1 because that will give me an odd term. So you should test and see if this works. So I look at that and I think, well, 2 times 1 would be 2. And then if I add 1, I would get my 3. So test that, see if that formula works. When we get to arithmetic and geometric sequences and series, we'll actually have some formulas to use to calculate what that equation looks like. So right now it's just kind of guessing, but when we get to the arithmetic, we have a definite formula to come up with that equation. Okay, so let's test this for now. So 2 times 1 plus 1 equals 3. 2 times 2 plus 1 equals 5. 2 times 3 plus 1 equals 7. 2 times 4 plus 1 equals 9. 2 times 5 plus 1 equals 11, etc. So I've verified that my formula is correct because all of my terms come out correctly. Okay, section 12.2 is on series. And a sequence is just that list of numbers. The series is actually when you add up the first n terms of a sequence. So now we have some notation that we kind of have to pay attention to. It's called summation notation or sigma notation. And you might see sigma on a spreadsheet package like Excel. If you wanted to sum a column of numbers, you'd click on sigma and it would highlight so that you could see the numbers and then just highlight the ones you want to add up. So it just means to add them up. When we look at this, n is going to be our index and to be our upper limit. So when we're looking at this, the x is the upper limit. So that tells us our a to wherever we are stopping. Then the 1 is the lower limit, so that's our starting point. So this is our lower limit, and it is where we are starting. And it is read, the summation from n equals 1 to x of a sub n. So let n take on values from 1 to 5 and evaluate the sum for these summation notations. So again, my lower limit will be 1. My upper limit will be 5. My formula is n squared. So now I want to add these together. So my first term is going to be 1 squared, then plus 2 squared, plus 3 squared, plus 4 squared, plus 5 squared. So here I'm starting with my lower limit and ending with my upper limit. Simply substitute in that index of summation, those numbers. So I get 1 plus 4 plus 9 plus 16 plus 25, which equals then 55. So that's all this notation means, is that you can generate this list of numbers and then sum them to come up with the sum starting from 1 to 5 of that sequence. Let's look at another one. Again, my lower limit will be 1. My upper limit is 6. And my formula is 1 plus n squared. So that will be equal to 1 plus 1 squared plus 1 plus 2 squared plus 1 plus 3 squared plus 1 plus 4 squared plus 1 plus 5 squared, and finally plus 1 plus 6 squared. So that will give me 2 plus 5 plus 10 plus 17 plus 26 plus 37. When I add those up, I get 97. So that's simply summation notation. And on a multiple choice test, you need to look very, very closely at those, especially on the final. Pay very close attention to the fact that the notation sums the sequence correctly. And all you have to do is substitute in those numbers to check that. Okay, converting to summation notation. So now I want to write this in summation notation. So this is going to be my first term. So I have 1, 2, 3, 4, 5, 6, 7 terms. So in my notation, I start with n equals 1 and end at 7. And when I look at this, I see they're all even numbers increasing by 2, and that makes me think of 2n. But I would test that just to make sure. So I have 2 times 1 gives me 2, 2 times 2 gives me 4, 2 times 3 gives me 6, and you see the pattern, etc. Okay? These are just some special formulas that actually were listed in the old textbook. They're not listed in the new textbook, and we can talk about some of these later. The I, once again, I told you that some textbooks will use an I instead of an N. That should be an N there. And this should be an N as well. This should be N equals 1. Let me make sure all those are correct. That's I. So as you see, what your index of summation variable should match the formula variable. I think they're all correct now. And that's actually all for the notes for today. So if you could take a look at a few of those problems on pages 773 to 774, 5 through 37, every other odd, and then page 778 through 780, 5 through 33, every other odd, and then 45 through 49. I don't think they're terribly difficult or terribly challenging. They're just asking you to rewrite something in summation notation or to identify certain things that we've talked about in these sections. Again, we'll go over more on sequences and series tomorrow. Thank you and have a good evening.